Recorded is rolling. It is Wednesday, September 3rd. Yesterday in class, I was going through these posters and I wasn't able to quite get to the last few, so I'll finish that here at the beginning of class today. There's a question that came up about relative velocity in my other classes, so I do want to explicitly cover this with you guys, and we'll go through an example here. Okay, and here's where my classes are doing different things. If you guys have your laptops, after I hit all this stuff, I'm going to open up a Kahoot on conceptual questions on linear motion. So see how you guys are doing there. And then, I did have some other plans, but my other class has been running out of time. So we might have to bump some of these other activities to a different day. We'll see how it paces out. Okay, so here, I'm going to skip through this a little bit. Okay, I guess this might be a good place to start. Okay. So you guys know there are these 5 kinematic variables we're juggling. Okay, we got time, we got displacement, we got initial velocity, final velocity, and an acceleration. Okay? And these 3 kinematic equations can handle those relationships. Oh, your linear motion puzzles, if you turn those in, then I do have those graded in the back in your folder, so if you want to see them. But everybody's turning in so far. You guys have been doing pretty good. So pretty straightforward questions that you guys are able to navigate these 3 formulas. So a quick recap here. The first one tells you the relationship between distance and time, or displacement and time, I should say. The second one between velocity and time. And the third one between velocity and displacement. So any one of these might be useful in any particular context. All right. So you got those. Okay. So a classic example in this class they keep returning to is drop a ball off a cliff. Right? So if you're watching time take 1 second at a time, let's see, this is in a constant acceleration field, which means that velocity is picking up at a constant rate, 0, 10, 20, 30, 40, 50 meters per second. Right? This is equals g times t. Isn't this like one of those kinematic formulas? V equals gt. Actually, it was like that second kinematic formula. It's like this one right here, starting from rest, right? 10 times however many seconds. Okay. Right? And then guys, how far the ball fell. Now, if I define the top of the cliff as 0.0, and how far after like positive is down. Okay? Who remembers, guys, trivia time, or maybe you remember, after 1 second, or maybe you can figure it out. Guys, after 1 second, how far will the ball fall? How far will a ball fall after 1 second? 5 meters? Just saying 5 meters? Yeah, 5 meters. Right? And it's actually any numbers in this column you can get from this top kinematic equation, which actually we can simplify. Because if you drop a ball, guys, drop means this number is equal to what?
0.
0, right? Because initial velocity would be 0. Right. Okay. And then for acceleration, can you call that 10 meters per second squared if you're on Earth? Right. And then 1 second. Let's try this out. Guys, 1 squared is 1. Half of 10 is 5. 5 times 1 is 5. Right? And of course, that would be meters in this case, if you also follow the units, right? So that's where this comes from. Guys, what if I plug in 5 seconds? How far will the ball fall in 5 seconds?
20 meters.
Or 5 seconds. Here, let's try it out. Okay, so this bit's 0, so this bit goes away again. Okay. Guys, what's 5 squared?
25.
25? And half of 10 is 5. What's 25 times 5? It's about 125 meters. How'd you know that, college? Hey, is that the college equation? Is that college equation? Is that how deep Colin Hewitt's Minecraft was? About 125 meters deep. How'd you know that, college? Yeah, that was right there. All right, so you got that. Right, okay, and then here's that exact same table of values, the same story, but now in a graph form. Okay, how far is the function of time? How fast is the function of time? And then acceleration versus time. Okay. So in an accelerating environment, don't the graphs tend to look like this? Right? Parabola, straight line, and constant. Right? Tends to, right? And then I think if I remember right, I may have just barely got into this one right as the bell was ringing. Right? So just try to pick up from here. Right? What if you don't drop the ball? What if you throw the ball? Now, this is still linear, so we're still just going straight up or straight down. So like straight or straight down. Right? So in that case, well, if I start from the bottom here, as soon as you release the ball is free fall, so it's accelerating the same, right? Now that doesn't mean it has the same speed. That's this middle graph here, velocity versus time, right? It's just if Earth's gravity regardless, as soon as you let go of the ball, okay? Now, if I define down as the positive direction, that means if you throw the ball down, you're giving it sort of like a positive intercept, right? If you throw the ball upward, you're throwing it in the negative direction, right? And then after that, guys, do these two graphs right here have the same slope as each other? Yes, they do. Now, actually, that slope is equal to what? Yep, gravity field. Boom. Same thing. Okay. Right. Now, the kind of tricky one is usually displacement versus time. Because this is, guys, are both of these right here? Are both of these curves? the same basic shape. Yeah, they're both what?
Parabolas.
Parabolas, both parabola. Right, right. Now, if you throw the ball upward, here, guys, if you take something, throw it straight up, doesn't it rise, go higher, higher, it slows down, and then reaches a peak, and then it falls back down? Right. So remember, if I'm defining up as the negative direction, then there's some like maximum negative distance it goes, and that would be in this case like the maximum height. Okay. Guys, what is the speed at the maximum height point? Zero. Should if this is the same time, should this align with 0 meters per second? Bing! Oh, it does right there. You guys see that? Max height point aligns with that 0 speed. Yeah, same thing. Right. And it speeds up on the way down. Right. Right. Okay. All right. So you guys good with these? All right. Oh, okay. If I take this one right here and blow it up, now it's big. So the velocity versus time graph in physics is very information rich. Tells you a lot. You can know the speed at any time. Just that's the coordinate. Somewhere on this black line, it's like some coordinate. You can know what is the slope of this line tell you? The rate change of velocity. That's called what? Acceleration. Yep. Right. And if you accumulate the area under the curve, so somebody's like kind of speed times time, you kind of think of it that way. Okay, speed times time tells you what's the area of this curve equal to. It tells you how what? Not how fast.
How far?
How far? Yeah, how far? Isn't this a distance right here? Right. Guys, can you add this rectangle plus this triangle? Let's see. V naught t plus half at t squared. Wait, where have I seen that? V naught t plus half at t squared. Hey, that's this guy right here. You guys remember that? Right. This tells you how far. That's the college equation right there. Right there. Got that. Okay, here's an activity I wanted to do today, but we'll probably have to bump to another day. What if you team up with a teammate, right? And one of you holds a ruler, the other has their fingers down here at the 0 centimeter mark. You guys see 0 centimeters right down here? Right. And then whoever's holding the ruler lets it go, and the other person catches it as fast as they can. Supposed to catch it at the 17 centimeter mark. Right? Hey guys, while the ruler was falling, is it accelerating in Earth's gravity field? Yeah, that's what a gravity field is, type of acceleration, at least at a local level. Right? So if you catch it at the 17 centimeter mark, for example, does that correspond to some exact amount of time that the ruler's been falling for? It does. And do you think you could figure that out? Right? Guys, hold on to this idea, because if we don't do this today, then probably tomorrow. I'll have you guys solve for time based on how far the ruler fell. Do you think you can figure that out? Okay. And maybe, what if I throw a blank paper at you guys? If I throw a blank paper, I say make a table. Do you think you could come up with a table like this and eventually figure out how much time? Or this would represent your reaction time, wouldn't it? Because is there a delay between what's happening in the world and your brain processing it and realizing what's going on? Yeah, but you can't sense it yourself because that's kind of the thing you're trying to figure out. Yeah, but with this you can. If your friend drops the roller and you catch it, ooh, you're about to find out what your time delay is. Right, car braking to a stop. Okay, if I had a lot more time with the guys, well, here, I'll do this anyway. Let's cover these 3 graphs so you guys can figure this out one by one. So, car brakes to a stop. Let's go, let's start with the middle graph. Usually do. Okay. Okay. Does the car at the beginning of this interval have a velocity? Yeah, because it hasn't stopped yet. Right. So what does that mean on a v versus t graph? Does it start at 0, 0? No, it starts at some positive intercept. You guys see it got a v naught up here, right? But at the end of the interval, it's at 0 speed. Is that true?
Yeah.
Right. So I got 0 something down here, or sorry, something 0. Right? Now, what kind of line do you think should connect those 2 points? What kind of shape do you usually see for velocity versus time curves in this class?
It's the kind of red.
Yeah, like straight lines. Straight lines. Okay. Okay. That's called I should really in the title throw uniformly in here. Brakes uniformly to a stop. Right. So that'd be a constant acceleration. In fact, guys, that acceleration. If I have a stick figure walking down, walking left to right, is he walking uphill or downhill? Downhill. That means it's a what kind of slope? Positive or negative? Negative. All right. So you guys just told me something about this last graph, acceleration versus time. What would that graph look like? Is this a constant negative slope right here?
Yes.
Okay. Is this going to be a constant negative value?
Yeah.
Okay. Same thing. Same thing. Here's that constant negative value. Okay. Finally, the tricky one. Oh, X versus T. You know what? Let's go ahead and do this anyway. You guys got some paper out, or some probably paper within reach. Gave you guys some scrap paper. Okay. See if you guys can draw the X versus T. Well, walk around the room and see who's able to draw that. Just worth their time to do. Okay. And yeah, so we got to take a note. So you have your notebook anyway.
We're drawing this upper back.
Yeah, you're much fun. Right. If I draw the one I got covered up, how far does the card go as a function of time as it's breaking to a stop? What is that? Ah, winner. Yeah, yeah. Yeah, X versus T. So distance versus time. All right, take one more trip around the room. Yeah, got it right here. Winner. It's Caitlin got it, Anna got it. It's gonna get the yeah, winner. That. Yeah, just like that. All right, got a few more winners. All right. Guys, well, look, yes, it's Bella got it. Gavin got it. Okay. Guys, while the car's breaking to a stop, is it still moving forward, or is it going in reverse? Still going forward. So I think the whole time it should always be kind of going out to the right. Like as time takes forward, going to the right, the car's still going forward. It never reverses. It never comes back. It's always going forward. Okay, but at a slower and slower rate. Okay. How about this? You guys remember? I've got labeled here that the displacement is the area under a V versus T. Suppose I break this apart into like 3 time intervals. What if this takes 3 seconds? Guys, imagine it takes 1, 2, 3 seconds to come to a stop. Okay. So during the first second, ooh, look at the size of that trapezoid. Is that a pretty big trapezoid? During the first second, that means the car moved a long way during the first second. But then, what about this middle second? Is that a shorter trapezoid? So the car's still moving forward, still accumulating distance, just not as much. What about this very last second where it comes to a stop? Is that a little itty bitty triangle right there? Itty bitty triangle? All right, so still moving forward, just a little bit. Okay. Now, if you plot that off, so we guys figure this out. Okay. You go a long way during the first second, kind of medium amount in the second second, and this last second, still moving forward just a little bit. Okay. Okay. Guys, what shape is this right here? Parabola. And guys, where's the vertex of this parabola? Is the vertex down here or is the vertex up here? Up here? You guys see up here? Yeah. Guys, this is the vertex. This point's the vertex. Okay. It's like an upside down parabola. Okay, I got one more poster for you guys. So, suppose you have some physics equation out of a book and you're trying to make sense of some story, like what exactly is going on. Okay. You got velocities, you got accelerations all over the place. Maybe it looks kind of like one of these or some of these. Right? And you're trying to figure out what's going on exactly. Now, the direction of velocity tells you the direction of motion. So if you're moving forward, velocity is always positive. If you're moving backward, velocity is negative. We'll say you're in a car for this, like moving forward or backward. Okay. Acceleration tells you something about how you're changing or how you're tending to change. Has something to do maybe with speeding up or slowing down, or something like that. Okay. I know in a fall off a cliff it has to do with like the gravity field or something. Okay. Okay. So let's go through these scenarios one by one. Okay. Because if you have positive velocity, that means you're moving which way again? Forwards or backwards? Yeah, forwards. So you're moving forwards if you find positives forward. Okay. But if you have acceleration that's also positive at the same time, not only are you moving forwards, you're moving forwards how? Are you speeding up or slowing down? Speeding up. Yeah, moving forward, speeding up. There you go. Okay. Now, what if you have positive velocity with negative acceleration? Which direction are you moving? Forward. Okay, yeah, so you're moving forward, but you're moving forward how? So slowing down? Yeah, slowing down. Moving forward, slowing down. Okay. In fact, that's exactly what we just did. Isn't this right here? You have positive velocities but negative acceleration. That's that one right there. Yeah. How about what if it's negative negative? Let's do this quadrant right here. Because if you have negative velocity, you're moving which way? Backward. Yeah, backwards. So now the car's in reverse. Right? And if the acceleration is also in the same direction, It's negative, negative. That means you're moving backwards doing what?
Slowing down.
Mm,
What? No, you're moving backwards, going for speeding up.
yeah, you're speeding up backwards.
Yeah.
Right. So you got the car in reverse, faster, faster, faster. Right, right. Because these signs are great. That's the rule. Is whenever you have plus, or minus, right, you're speeding up.
Yeah, two negatives make a positive.
Yeah, it's sort of thinking that way, right? Yeah. And then how about this last quadrant? If you have negative velocity but positive acceleration, that means you're moving backward, like braking to stop or slow down. Right. Okay. Okay. So yeah, if the signs are the same, plus, minus, that's a speeding up condition. If the signs are opposite, like plus, minus, plus, that's always a slowing down condition. Okay? And the direction of velocity always tells you the direction you're actually moving relative to something. Okay. Okay. So you guys good with this? Okay. So the other point I want to hit here for the Kahoot is relative velocity. Okay. So I'll give you guys a one-dimensional example. Okay. Let's say we're up in a helicopter. We're looking down on I-95. You see I-95 right here? Okay. And I see a couple of cars. I see a black car right here. And I see a pink car right here. Black car versus pink car. Okay. Now, these cars have different speeds. Right? The speedometer readings are showing different numbers. Okay. Let's say that the pink car is going, I'm going to use American units. Let's go 60 miles an hour. And let's say the black car is passing, let's say it's in the passing lane. Let's say it's going 70 miles an hour. Okay. Now, already, guys, those velocities. See, if you were sitting inside the car, suppose you're blindfolded in the passenger seat in the black car. Can you feel it? Oh, it feels like I'm going 70 miles an hour. Is that something you can feel?
No.
No. You feel accelerations. Don't feel speeds, right? Because these velocities are relative to something. I'll tell you what they're relative to. They're relative to this tree right here, or I guess, or the road, or anything else, right? Something to the outside world, right? If our helicopter is just stationary, maybe it's relative to our helicopter. If there's a monkey in this tree and he points a radar gun at these cars, his radar gun reads these numbers. Okay, okay. Now, since this is this is about here, I should give you guys a title: relative velocity. Right, is the idea I'm trying to cover here. Right. So, what is the velocity of the pink car relative to the black car? And then what is the velocity of the black car relative to the pink car? Right, you'll feel a little vector arrows here. Okay. And then you can figure this out logically, and then I'll show you more formal way to do this. Right. So the pink relative to the black. Right. Actually, let's start with this one. The black relative to the pink. So this is if you're sitting inside the pink car, and for your purposes, in physics terms, you may as well be at rest in the pink car at constant velocity. Okay. How fast does it look like the black car is going relative to you?
10 miles?
10 miles per hour. Yeah. If you point your radar gun out and put at the black car, it doesn't read 10 miles per hour. Okay. And how about the other one? What's the pink relative to the black? So if you're inside the black car, to you, it looks like the pink car is doing what? Negative 10. Well, it's constant velocity, but it'd be negative 10 miles per hour. Right? Right. Guys, what if these were spaceships out in deep space? We're all just floating around. Actually, would you be floating around in deep space? Deep space floating around? Yeah. Constant velocity is the same as being at rest. Okay? Constant velocity and being at rest are like physically identical. Right? Right? There's no way to sort of distinguish the difference. Okay? Yeah. So if inside this pink spaceship, it would look like the black one was moving at 10 miles per hour. And if you're inside the black spaceship, maybe you feel like you're at rest and it looks like the pink is moving this way at 10 miles per hour. Right? Okay. So the formal way to get this is, so the pink relative to the black, you always take the other guy's velocity, in this case 60 miles per hour, for the pink, okay, and subtract your own velocity, which for the black would be 70 miles per hour, okay, to give you negative 10 miles per hour. Okay. But from the pink's point of view, you take the opposite velocity, which is now 70 miles per hour, subtract your own, which is 60 miles per hour. And that gives you positive 10 miles per hour. Okay. Now, this is a one-dimensional example. You can also take this to 2 dimensions and 3 dimensions. Right? You just subtract velocity vectors. Okay. Take the other guy's velocity vector, subtract your own velocity vector. I'll spell that out while you guys are writing this. Right? Take the other velocity vector, and subtract your own velocity vector. Okay, so when we eventually go to two dimensions and practically you can do the same thing. This is called relative velocity. Okay. All right. So guess that ever shows up. Boom. All right, I'm gonna close down this recording and get a Kahoot going.